Welcome class to our Skill 1 guided notes from Unit 3. In this video we will be covering part 1 of Skill 1, which is just the graphing part. In the part 2 video is when we will talk about all of the defining characteristics. So in Unit 3, the main function that we will be studying is called the reciprocal function. It got its name because of the fact that you basically take the reciprocal of x to get y. Or, in other words, y and x are reciprocals of each other. So this is the parent function here where it's just 1 over x. And then also in this video, we'll be looking at graphing transformations of this parent function in this form, we call it hk form, a over x minus h plus k. As with all of our parent functions, one of the very first things we do is to just try to understand it by plugging in values for x to see what the y values are like and how they behave and get a general sketch of the parent. Notice that for this parent function, I have added a couple new points, -1/2 and +1/2, because of the reciprocal nature of this function, and I want you to kind of notice something about what y does when x gets small versus what y does when x gets big. So we needed some quote-unquote small numbers to kind of notice or observe this first feature. So basically, the y value of this function is just the reciprocal of x. So you kind of just think of it as 1 over x. So the reciprocal of -2 would be -1/2. And then the reciprocal of -1 is just -1. But the reciprocal of -1/2, when you divide by a fraction, you basically multiply by its reciprocal. So the reciprocal of -1/2 is -2, or 1 divided by -1/2 is -2. So you basically just flip x over. That's how you get y. That's what 1 over x means. 1 over x means flip it over. If it's -1 over 2, the output will be -2 over 1. Now, an even more special thing happens when x is 0. I'm going to give that one multiple stars because something very, very interesting and different happens to this function when I sub in 0 for x. I end up with basically a 0 in the denominator. And this was something that we kind of analyzed earlier in class today when you take the number 1 and divide it by a number that's getting smaller, approaching 0, getting closer and closer to a tiny number of 0, actually produces a very large output. So in a very loose sense, this is not technical, but in a very loose sense, when you try to divide by 0, you're producing a very large number. Technically, the value doesn't exist. 1 divided by 0 does not exist. We have no set value for that. And so what's happening on the graph of y equals 1 over x is this thing called a vertical asymptote. A vertical asymptote. It is a dotted vertical line that goes all the way through the x value of 0, which also happens to be the y-axis. So all along the y-axis, there's this dotted vertical line to indicate a couple things. The first thing is that the y value doesn't exist because 0 ended up in the denominator. But as you'll see when we go to graph the points, the y values are getting really big in the positive direction or really big in the negative direction around that vertical asymptote. So we're going to notice that as x gets smaller, y gets bigger. That's a reciprocal relationship, right? Y is the reciprocal of x. So if x gets small, y gets big. When x was -1/2, y was -2. And then here, when x is +1/2, so 1 divided by 1/2 means 1 times 2 over 1, or 2. Because dividing by a fraction means to multiply by its reciprocal, and 1 times 2 is 2. Other way to think of it is y is just the reciprocal of x. So if x is 1 over 2, y is 2 over 1. So when x gets small, y gets big. And that's what's happening around this vertical asymptote. Okay, then I'll plug in the numbers of 1 and 2. 1 over 1 is just 1, and 1 over 2 is 1/2. So when x gets bigger, goes to 2, y gets smaller, goes to 1 over 2. If x were to go all the way to, say, 100, the y value for that would be 1 over 100, small, right? As x gets big, y gets smaller. So there's another sort of loosely translated definition here that can help illustrate that. So it's kind of like this. X is in the denominator of the fraction, right? Y is 1 over x. So if I were to plug in something that's getting infinitely larger, something that keeps getting bigger, 10, 100, 1,000, and so forth, then if you take the reciprocal of that number, right, when x was big, 100, and then you take the reciprocal of that number, 1 over 100, or 1 over infinity, the value gets really small, right? 1 over 100 is a value close to 0. It's 0.01, which is not far from 0. So this is sort of like a loose understanding of what this means. When I divide by a large number, the result is a small number. And when I divide by a small number, the result is a large number. This here is why this function has a vertical asymptote. And this one down here is why the function has a horizontal asymptote. So we talked about that in class earlier today as well. That's kind of happening toward the ends of the x-axis. The y values get closer to 0. X goes to infinity, but the y values get closer to 0. So we happen to have this horizontal asymptote, this end behavior of 0. So this vertical asymptote is because x is getting bigger, is because x is getting smaller, x is 0, y is getting bigger. That's what's happening at the vertical asymptote. The horizontal asymptote, now the y is small, right? So x is getting bigger. That's what the horizontal asymptote is representing. And then the y goes to 0. The y gets smaller. So these are going to kind of outline or define the rest of our graph. And then I'm just going to plot the rest of these points. So I have a point at -2, -1/2, -1, -1, and then -1/2, which is right here, down -2. So it kind of forms kind of like the shape of a boomerang, for lack of a better word. It just sort of looks like a boomerang. It is curving through the points. It's not sharp and straight, it's curvy, and it's reaching out toward these asymptotes, both the horizontal one and the vertical one. And then at 0, the function breaks. The points to the left of 0 do not connect with the points to the right of 0 because of what's happening at 0. There was a vertical asymptote. So really this function consists of 2 disconnected parts. So now we're going to do the second part with the point at 1/2, 2. So x is small, y is big. 1, 1, that's where they meet up, is when x is 1. And then 2, 1/2. So x gets bigger, y gets smaller. And then again, it's like an opposite facing boomerang on the right side. This boomerang kind of opens down. This one sort of opens up. They kind of stick to their own parts. This one's in quadrant 1, this one's in quadrant 3, and they both reach out toward their asymptotes. So this parent function has what's called a point of symmetry. That point of symmetry is right here where the 2 asymptotes meet. So that's what I'm going to put here. It's where the 2 asymptotes meet. Right at that point, this boomerang here on the right could rotate 180 degrees and map onto the boomerang on the left. You can kind of visually see that too. Like this point, if I rotated it 180 degrees, which basically makes a straight line, would map right onto that point, right? This point, if I rotate it 180 degrees, which makes a straight line, would map right onto that point. This one here, again, rotated 180 degrees, which is a straight line right through that origin there, would map right onto that point. And same for all the rest of the points along both sides. If you rotate any of them 180 degrees, you'll find the corresponding point on the other part of the graph. So we say that this graph has point symmetry through the origin, 0, 0. This part could rotate 180 degrees and map right onto that part. Okay. This graph has neither an x-intercept nor a y-intercept because the vertical asymptote happens to be along the y-axis and the horizontal asymptote happens to be along the x-axis, and the graph is not able to touch or cross either of those asymptotes, and so it won't ever intersect either. And then, like basically all of our nonlinear functions, the rates of change along this graph vary, right? This one went down 1/2 and over 1, but this one went down 1 and over 1/2. And then from here to here, it's going down 1.5 over 1.5. So it's different slopes from between different points, so the rates of change will vary. The graph is 1-to-1 because it slightly angles over here and here, right? It's reaching toward those asymptotes, moving at an angle. The other way to think of that is it passes the horizontal line test, right? That's what lets us know it's 1-to-1. And it passes the vertical line test as well, which tells us it's a function. So the answer for this is yes. And then this graph will have neither a max nor a min because it is either strictly decreasing or actually this one's strictly decreasing the whole time, but it never changes from decreasing to increasing and vice versa. So it will never have a max or a min. The domain and range for this function is interesting as well. It includes almost every value. It's just it excludes 1. So we say all real numbers except when x is 0. X cannot be 0 for this function because when it is, bad things happen, the y value doesn't exist, and there's a vertical asymptote there. Similarly, for the range, every single y value is allowed and exists except for the y value of 0. Because, it kind of goes back to this, because the only way to get a y value of 0 maybe is if I plugged in 0 for x, but the y value isn't 0, it just doesn't exist. And then the reciprocal of any other x value is never going to be 0. So 0 just is not in the range. It's not in the domain and it's not in the range. Every other real number is though. So we kind of write all real numbers except x can't be 0. And then for the range, all real numbers except y can't be 0. The vertical asymptote for the parent function is at x equals 0, right? That's this vertical line here. But in general, when we start transforming them, it'll always depend on h. And the horizontal asymptote for the parent function is at y equals 0. That's along the x-axis. But when we start transforming the graph, that will be at k. Now, for increasing and decreasing, it's really, again, kind of strange for this function because there's these two separated parts. If you look at this part on the left, and remember, for increasing and decreasing, you always read the graph from left to right. It always goes from -infinity on the x-axis to +infinity on the x-axis. You read it that way. So I have to look at this left part first. And I notice that if I start at -infinity and move toward the right, these y values are decreasing. In fact, they're going to go all the way down to -infinity. But that's as x is wanting to go to 0. So my first interval for decreasing is from -infinity to 0 on the x-axis. And that is referring to this part of the graph is decreasing. Okay. But then if you look at the right side of the graph, so again, the graph breaks at 0 and a whole different part exists on the right. And so you could say, if you look at that part as x goes from 0 to infinity, right, moving from right to left, from left to right, the y values are starting at this infinitely high positive, and then they're moving down. They're getting closer to the x-axis, which is where y is 0. They're moving closer and closer to y is 0, which means technically they're decreasing the entire time. So there's a second interval for decreasing, and that starts at 0 and continues until infinity. And the function is basically never increasing. This is for the parent function, but a similar thing will happen for all the other ones, is there will be two intervals, right? They will split over where the vertical asymptote is. So wherever h is where the intervals will split. And either both of them will be under increasing or both of them will be under decreasing. So, and that's the case here. This function is technically decreasing for both parts. And the thing that's weird, I know, is that like to the left of 0, the y values are negative, but then on the right side of 0, they're positive. So one could argue, well, they increased right there. And the argument is, well, not really. The graph changed. The graph just is it's just different on this side. So basically, we never include 0, right? We just say to the left of 0, it decreased, and to the right of 0, it decreased. At 0 was an asymptote, and so we don't really count it as having increased there. Okay, so that's the parent function. So to graph transformations of the reciprocal function, functions of this form, we actually follow the same rules that we followed for quadratic and cubic and absolute value graphs. In fact, I kind of want to show you one thing right here. You could think of this HK form as looking like this. A in front, the reciprocal function with h inside the parentheses plus k. If you think of it that way, because these are really equivalent, if you think of it this way, then it looks a lot more like the other HK equations we've had where it was like a parentheses something plus k. That's really how this began. A times the reciprocal of x minus h, done, and then plus k. It's just that you can think of this as a over 1, and when you have two fractions being multiplied together, you just multiply straight across, so that's how the a ends up in the numerator, is because it was being multiplied to the fraction, and so it ended up in the numerator. And so because the a value multiplies to the y value, it has the ability to reflect, stretch, or compress the graph, just the same way it did for quadratics, cubics, and absolute value. And the h value, which is thought of as the thing inside the function, in this case it's in the denominator with x, it adds to the x coordinate and therefore moves the graph right or left, but we have to remember it's always the opposite sign from what you see in the equation. And the k value, which is thought of as being outside of the function, right? Usually it's after the parentheses. It's adding to the y value, and so it moves the graph either up or down. That was the same, again, with all of our other parent functions. And for graphing these functions, the steps will be very largely similar to the other ones we've learned, except for the fact that these reciprocal graphs have what we call asymptotes, right? Vertical and horizontal asymptotes, which add another layer to the graphing. And so I usually have students identify those first because they provide a nice sort of boundary for the rest of the graph. And then notice I have that also in step 5, dot in your asymptotes as well as graph the new points. But the way we find the points is essentially the same. You do a table of values for the parent function, and then you transform those values by adding h to x, multiplying a, and adding k to y. So let's try that with a couple examples. So let's start with this first one here, with example 1. Looking at the way the graph is set up, I can see, with the way the equation is set up, I can see that a is 1, h is 2, and k is 5. So something I noticed right away is that my point of symmetry will be at 2, 5, right here. That is where the middle of the graph will be. That is also the point where my asymptotes intersect. Okay, your asymptotes will intersect at the point h, k. So then that causes me to also realize, well, then the horizontal asymptote, the one that's going this way, it must go through the y value of 5. Okay, and the vertical asymptote, the one going vertically, must go through the x value of 2. And that is in fact the case. So the vertical asymptote will be based off h, and the horizontal asymptote will be based off k. Now, I want to explain why. Why is it always that way? And this is unique to the reciprocal function. So the vertical asymptote occurs when the denominator is equal to 0. Okay? When you end up having a number divided by 0, that leads to a vertical asymptote. So what we look for is the denominator, which in this case is x minus 2. And we set that equal to 0. When we solve that equation, we find, okay, x equals 2. That's the value of x that causes my denominator to be 0, right? If I plug 2 into this equation up here, I get 1 over 2 minus 2 plus 5. That turns into 1 over 0 plus 5. This value does not exist, therefore none of it exists. Does not exist. And again, it's because we were dividing by 0. So when the denominator equals 0, that's where you'll have your vertical asymptote. And because h is always the number being subtracted from x in the denominator, that's why h always ends up being the value that causes the denominator to be 0, which is why it's our vertical asymptote. So this is the whole x gets small relationship causing that vertical asymptote. The horizontal asymptote is caused when x gets big. So when x gets big, we're talking, in this case, y would be 1 over big, okay? 1 over infinity plus 5, right? Because even though you're subtracting 2, you're subtracting it from like a gigantic number. So gigantic number minus 2 is just some other gigantic number. And when you take 1 and divide it by a large number, we looked at that in class today, that quantity goes to 0. So the bigger x gets, the more I'm adding 0 to 5. And 0 plus 5 is 5. So y gets closer to 5 as x gets bigger. Now that's always going to be the k value, because the k value is the thing getting added to the fraction, and the fraction's getting smaller and smaller when the denominator gets bigger. So this fraction's becoming 0. You add that to 5, and that's your horizontal asymptote. So that's the reason behind it. If that's still hard for you to understand, which is understandable, then you can remember x equals h, that's your vertical asymptote. That's when your denominator is 0. Y equals k would be your horizontal asymptote. It would be what would be left over for y as this fraction, as the denominator in the fraction gets increasingly large. Okay, but you can see here it serves a very nice boundary for our graph, and I can kind of picture those opposite facing boomerangs. But I'm going to make a table of values though to find them for sure. So I'm going to start with x and y. I'm leaving some room so that I can add h and k to these values. And I'm going to use, I'm going to include the negative 1/2 and 1/2 here because I think it helps when we're new to this. And then y is just the reciprocal of all of those values, and then it doesn't exist. So taking the value of 1 over 0 does not exist. So this is where the vertical asymptote is, okay? I'll just call it VA for short. And then when x is a fraction, you flip that over, you get y as a whole number. Reciprocal of 1 is 1, reciprocal of 2 is 1/2. So these are the x and y values from the parent function that we looked at a moment ago. And what I'm going to do is I'm going to add h to all the x's, multiply a to all the y's, and add k. So I just add 2 to all of these x's. And then I add k to all of the y values. And so this will be 0, 1, 1.5, 2, 2.5, 3, and 4. These are my new x's from the transformed graph. Everything moved to the right too. My k value will be 4 1/2. Not my k value, sorry, my y coordinate. 4 1/2, 4, 3, nothing here, right? Vertical asymptote. 7, 6, and 5 and 1/2. So when I plot these points, I'm going to make sure I do not connect the side to the left of the vertical asymptote with the side to the right. So it's really important that we identify there is a vertical asymptote when x is 2, right, at this h value right here at x equals 2, and I cannot cross over it. So I'll plot these points on the left, 0, 4 and 1/2, 1, 4, and 1 and 1/2, 3. And then I just remembering from the parent function, it kind of looks like this downward facing boomerang on the left. Okay, now these points do not connect with the points on the right. They just reach out toward the asymptote on either side. Just have it kind of stretch out at an angle toward both asymptotes. On the right side, I have a point at 2.5, 7, 3, 6, and 4, 5 and 1/2. And then I make that opposite facing boomerang on the right side. Again, I don't connect the points on the left and right. I just have each side reach out toward both asymptotes, and they look sort of like opposite facing boomerangs. The transformations will be that this graph moved to the right 2 and up 5. So let's take a look at example 2. And looking at the way it's set up, I can see that my a value is -3. And I'm looking in the denominator, and all I see is x. I can think of that maybe as x minus 0 if that helps. But basically, because only x is in the denominator, we can think of h as 0. K will always be the number being added to or subtracted from the fraction itself. So k is -4. Okay, so I have my a, my h, and my k. Now, I always encourage students to look out for the asymptotes first, right? H is the one that determines the vertical asymptote. K is the one that determines the horizontal asymptote. So I have a vertical at x equals 0 and a horizontal at y equals -4. A quick review for both of these. The vertical asymptote occurs wherever the denominator is equal to 0. And in this problem, the only thing in the denominator was x. And so when x is 0, the whole denominator is 0, which is where the vertical asymptote will be. So this, like the parent function, will not cross the y-axis. It has a vertical asymptote there. The horizontal asymptote has to do with when the x value gets big. When x gets big. And when I say big, I mean big. 10, 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, big. Okay? Now when x gets big, what happens is the fraction gets small. So -3 over infinity minus 4, this part would get smaller and smaller and smaller. It would go to 0. And then 0 minus 4 is -4. So since the fraction basically goes to 0 when the denominator of it gets really large, then it's like you're just saying 0 minus 4 for y, right? The y value that remains would be 0 minus 4. And so that's what y is approaching, getting closer to the bigger x gets. So it's our horizontal asymptote. Okay, so we dot those in to act as a guide for the rest of our graph, okay? So then we work on the on the table of values for the parent function, and then of course the transformed one as well. And so I'm going to use these x values here. The y value for the parent function is just the reciprocal of the x. I just flip my x's over, and then that's my y. So when x is 1/2, y is 2. When x is 0, y does not exist, right? This is where our vertical asymptote will be. And when x is 1/2, I flip that over, I get 2 for y. When x is 1, y is 1. And when x is 1/2, or sorry, when x is 2, y is 1/2, 1/2. Okay, So that's the parent function. Then I add h to the x's, which is just 0. So it's not going to change any of these x's. So these are the same x's that will be for the transformed graph as well. For the y's, I will multiply by -3 and then subtract 4. So the y is going to have a lot of changes to it. Multiply by -3, subtract 4. So here, this becomes 3 over 2 minus 4, which is 1.5, minus 4, which is -2.5. And here, this becomes positive 3 minus 4, which is -1. Here, I get positive 6 minus 4, which is 2. And that's 1/2 of the graph. Then there's the vertical asymptote at x equals 0, right? Cross over that, and then on this side I have -6 minus 4, which is -10. -3 minus 4, which is -7. -3 over 2 minus 4, which is -1.5, minus 4, which is -5.5. These are the points for the right side of the graph. So I will go ahead and plot them and be mindful of my asymptotes as I do. So I have -2, comma, -2.5. So that's like right here. -1, comma, -1. That's like right there. And then -1/2, comma, positive 2. So right there. So this time, the left side of the boomerang, or the left boomerang, is above the horizontal asymptote. That is because of the fact that my a value is negative. It's creating a vertical reflection. Go ahead and write that down right now. So the boomerangs, if you will be flipped. The one that's usually up here on the right will be on the bottom. And on the left, the one that's usually on the bottom will be above the asymptote. It'll be on the top, looking kind of like that. You also might notice it looks like kind of stretched, right? Pulled away. It's not as close to the asymptotes as our other graph was. That's because this graph also was stretched, right? It had a vertical stretch of 3. So the negative part reflected the graph, flipped the boomerangs around. This side's going to go down, that side's going to go up. And then the 3 stretched the points and pulled them further away from the asymptotes. Okay, but that's just the left side. Let's keep going. So when x is positive 1/2, y is -10. My grid only goes to 7, so we'll just have to kind of estimate roughly where that would be, right around there. When x is 1, y is -7, so that's right there. And when x is 2, y was -5.5. Right there. We get a similar shape boomerang on the right side here, kind of like that. And we want it to reach toward the asymptotes, right? Form kind of that curvy shape. It's all stretched out as well because of the 3. And it looks kind of has that same look as the parent function. But this graph also moved down 4. Right? The center of it is at 0, -4, that point of symmetry, right? Where the asymptotes cross. And it's flipped around the horizontal asymptote. So it had a vertical reflection and it vertically stretched by 3. Now, I'd like you to try a few graphs on your own right now. Wherever you are, I'd like you to pause the video and see if you can sketch this one. Pretty straightforward. This one, not as straightforward. There's a little trick to it. And same here, this one. You have the tools. Let's see if you can try them. Pause your video, come back. I'll have the answers ready, and then we'll have some practice in class tomorrow. Okay, let's check and see how you did. Hopefully for this third one, you found that A was 4 from right here, H was 2 from right there, and K was 1 from right here. So the H is 2 tells us the vertical asymptote will be 2. K is 1 tells us the horizontal asymptote will be 1. And the point HK is where the asymptotes cross. So I've got x equals 2 here and y equals 1 there. This is how I found the rest of the points that you see plotted. I took the x and y values from the parent function, added 2 to each of the x's, added or multiplied each of the y's by 4, which vertically stretched them, by the way, right, by 4. Also added 1 to each of them. And so these were the values that resulted. Here's my points plotted on this side and that side. And that was the graph for number 3. Also, you can always check these graphs on Desmos as well if you don't have an answer key available right when you need it. Okay, for number 4, this was tricky, right? This was kind of I wanted to see if you could kind of figure it out. Basically, what's happening here with 1 over 2x, sometimes students would say, oh, okay, 2 is in the denominator with x, so it's h. But remember, h is something that adds or subtracts from x, not multiplies. The fact that it's 2 times x indicates that's multiplication. So technically, what was happening here is it was 1/2 times 1 over x. So a was 1 divided by 2. So whenever there's a vertical shrink, a ends up in the denominator with x. Kind of an unusual case and also kind of tricky. Now, because there was nothing adding or subtracting to x down here, h is just 0. And since there's nothing adding or subtracting after the fraction, k is also 0. So the point of symmetry for this one was at 0, 0, right at the origin. And also both of the asymptotes were right on the x and y axis, just like the parent function. X equals 0 for the vertical, y equals 0 for the horizontal. Over here is basically how I got my points. The x's didn't change at all, and the y's just got shrunk by 1/2. So they're all like 1/2 the size that they normally would be. So they were -1/4, -1/2, -1 on the left, +1, +1/2, +1/4 on the right. You can see when you shrink a reciprocal graph, the points get closer to the asymptotes. That's an indication that it's been vertically shrunk. Tricky one. So if you got that, good job. Okay, B, also sort of deceiving, right? The way it's set up here, sort of deceiving. It looks like k is -2 because we're used to having k come second and this is following a negative, but technically the 2 is positive. It's the 1 over x that's negative, right? So it's better to write it in AHK form. Put the fraction first and the number second, and then we can see, oh, wait a minute, a is negative. It's -1. H is 0 because nothing is in the denominator adding or subtracting to x, so h is 0. K is positive. It's adding 2, right? +2. So k is positive 2. So there is a vertical asymptote at x equals 0 based on h, and a horizontal asymptote at y equals 2 based on k. So I have x equals 0 graphed here, y equals 2 graphed there. And the point where they intersect, obviously 0, 2, hk. And then here are my table of values for the rest of the points. I didn't have to change the x's at all. I had to multiply the y's by -1 and then add 2. Here are the points that resulted, so you can check and see how you did. This graph had a vertical reflection, and then it also shifted up 2. So hopefully you were starting to kind of get the hang of these, but we have all class period tomorrow to practice some more, and I'll see you there.